We are working on number 9, part B from the homework assigned during week 2. And we're trying to determine why the given statements in A, B, and C are false. So we're trying to find specific values in our domain, which is all integers. So we want to find specific values of x and y that show that this part B, this statement, is false. So first we need to understand what the statement is saying to find these counterexamples. So what I'm going to do is just write out each symbol's meaning piece by piece. So for all, the upside down A means for all, and x is an integer. So I'm going to write for all integers, x, there exists an integer y such that y squared is equal to x. So what this is saying is pick any integer. I can find another integer such that when I square that integer, I get x. So sometimes you're not quite sure what the counterexample might be, and so you can just kind of play around with some values. So notice that I'm picking x first, so let's just try x equals 1. Well, y equals 1, y squared equals 1. So this satisfies the conditions. However, it's saying this has to work for all x. So you need to keep trying. If it says there exists x, there exists y, then you would be done and it would be a true statement using this example. But we want to show this works for any integer that I choose. So let's try another integer. Let's try x equals, well, or even just a negative value. Let's try x equals -1. Well, I know that any integer that I choose and square it, it's always going to be positive. So this tells me that I know that there does not exist a y such that y squared is equal to -1. And because that's not true, this is a counterexample. If x is equal to -1, that's an integer. -1 is an integer. But no integer squared is going to give us a negative value. If we have complex numbers, then we'll find that a complex number squared gives us -1. I will, right? But since our domain is just the integers, we know that x equal -1 is a counterexample, and this is not a true statement. Let's look at C now. This is a pretty strong condition here for all x, for all y. Just like in A, this means if I pick any combination of integers, I should be able to show that this inequality holds. So this is saying if I choose any integer x, any integer y, if I take the product of x, y, it's always going to be greater than x. So again, just kind of play around, just pick 2 integers at random. So let's try x equal 1, y equal 2. Well, x times y is equal to 1 times 2, and that's 2, and x is equal to 1, so it's definitely true. X, y is greater than or equal to x. So that works in that example, and this is why it's really important to not just try one example when you're trying to prove a statement, because it's not enough. We're saying this is true for all integers x and y, and so it's not enough just to give a few examples that have a true value for the given statement. You have to show it for every single thing, and so we need to find just one counterexample though. So try to think of a case where I could multiply an integer by some number but get a smaller number back. And so I think about negative values. If x is, let's say, 2, but y is -3, then x times y is equal to 2 times -3. That's -6. but x is 2. So 2 is definitely not less than -6. So in this case, xy is not greater than or equal to x. It's less than. So this is a counterexample, this x and this y. This is a counterexample to the statement showing it's not true. Now let's look at number 10. We've got some statements involving the empty set and just different set notation. On part A, we're trying to figure out, is it true or false that the empty set is equal to the set containing the empty set? Because I know if A equals B, then the cardinality of A must equal the cardinality of B. Because they have to have the same exact elements, so then they must have the same exact size. So when I'm looking at this set equality, if this is true, if the empty set is equal to the set containing the empty set, then we must have the cardinalities to be the same. So I know that by definition the cardinality of the empty set is 0. There's no elements in that set. However, the cardinality of the set containing the empty set, that's actually 1. That set contains 1 element. Even though it's the empty set, it's still an element. So since their sizes are not the same, they don't have the same number of elements, I know that this is a false statement. And the same story works on part B. The size of the set containing 0 is 1. There's 1 element in that set, and it is 0. 0 is the only element of the set containing 0. But the size of the empty set, by definition, is 0. So since the cardinality is not equal, then I know the sets aren't equal. Because notice with the contrapositive of this statement, it would be if the cardinality of A is not equal to the cardinality of B, then A is not equal to B. Okay, so we can conclude that part B is false as well. Now let's look at part C. Now we're saying the empty set is a subset of the set containing X. And this is true for any set, actually. The empty set is always going to be a subset of the given set. However, let's just kind of understand the definition of subsets so that we can prove that this is true. We've got A and B in the same universal set. Let's see, A is a subset of B if and only if for all elements X in our universal set, if X is an element of A, then X is an element of B. So if we were try to prove that the empty set is a subset of the set containing X, the way that we do it is to pick an element in the empty set and show that it also has to be an element in the set containing X. So let's just write a little proof here that this is a true statement. Part C is true. So I'm going to start by writing out the definition of this subset. These subsets. So I'm going to say if the empty set is a subset of the set containing X, then for all elements in the universal set, if Y is an element of the empty set, then Y must be an element of the set containing X. The statement Y in the empty set is always false because there is no element in the empty set. So the statement for all Y in our universal set, Y is in the set containing X, is vacuously true. So this just means that since we have a false hypothesis, our implication is always going to be true. So I know that I can conclude that the overall statement that shows that we've got a subset is true. So therefore, the empty set is a subset of the set containing X. So on page 120 of the textbook, if you've got it, there's a well-written proof of this, so if you want to read that over to better understand. But the idea here is this is true. And I don't expect you to do a proof for this, to just kind of justify that I know that I'm starting with a false hypothesis and use this definition of subset, and so therefore it's vacuously true, and these two sets are subsets. Let's look at part D. And again, on part D, we're going to have to think about, I'm going to put part D over here. So D, we're trying to determine if it's true or false that Y is a subset of the set containing Y. So I'm just going to use the definition of subsets. This says if I've got any element X in my universal set, if X is an element of Y, then X is an element of the set containing Y. Now, Y, it does not have any defined elements. And if we look at the set that we're dealing with, it looks like Y itself is an element and not a set. It's possible that we could define lowercase y as some set containing a specific number of elements, but just Y alone doesn't give us enough information to determine if it's a set or not. So within this context, I think it's safe to assume that they mean the element Y and not the set Y. And so if we don't have a set, we can't determine what elements are in that set because it's just an element. So I can't say there is an element in the element Y. I can say there's an element in the set containing Y, but not in Y itself. So since I can't really go about this first part, this statement is false. This has to be a relationship between two sets, and Y alone is not a set. For part E, we're looking at the set containing X is an element of the set containing X. So if the set containing X is an element of the set containing X, then if we look at the set containing X and list the elements that live there, I should show the set containing X. Now, the cardinality of the set containing X is 1. So the only element in the set containing X is X itself. And if I list anything else, I'm messing up with the cardinality, because I can say that the set containing X is an element of X and the set containing X. But then notice the cardinality of this new set here is 2 versus 1 here. So this is a false statement because the set containing X is not listed in the set containing X. Only X is set there. So maybe the statement that is true, though, a set is always a subset of itself. Because if I pick an element here, it's always going to be here because it's equal. And so then I've satisfied the conditions of subsets. So this is a true statement, and this is another true statement. Now let's look at number 11, which talks about cardinalities of sets. So to determine cardinalities of sets, we just need to write out any elements that are in the given set to try to figure out how many there are. And we get more complex with sets. Now we're just going to look at these finite, easily understood sets. So for part A, just by definition, the empty set contains no elements. For part B, let's go ahead and list what elements we have. A is an element, B is an element, and C is an element. So that tells me, since I can list 3 elements, A, B, and C, the cardinality of that is 3. For part C, if I list all the elements, I've got A, I've got B, I've got C, and I've got the set containing A, B, C. So I've listed 4 elements. That tells me that my cardinality is 4. On part D, if I list my elements, I've got A, the empty set, and the set containing the empty set. Remember, the empty set is not equal to the set containing the empty set, so I need to list both of those. If I had something like A AB, the cardinality of this is just 2. It doesn't make sense when you're describing a set to list an element twice, because each element can either be in the set or not. It can't occur more than once in terms of these sets that we're dealing with. So this just doesn't make sense, but you would say the cardinality there is just 2. But so for part D, we've listed 3 elements, so that tells me the cardinality is 3. Part E looks like we've got 3 elements. We've got A is an element, the set containing A is an element, and the set containing A and the set containing A is an element. So the cardinality of this is 3. All right, now we're given some sets R, S, and T, and we're trying to do some set operations. It might help to draw a Venn diagram of all of this information that you're given on R, S, and T. So what I'm going to do is just draw a 3-set Venn diagram, and I might actually steal one so that it looks R, S, and T as my sets. Okay, so let's see. We've got to kind of work from the inside out. So to start, I need to know if I've got any elements in region 1. And so if I had elements in region 1, they'd have to occur in R, S, and T. But since T is the empty set and it doesn't contain any elements, I'm just going to cross out these regions here. So there's no elements in T. There must not be any elements in this region here, which contains the intersection of all R, S, and T. So in region 1 there is no elements, and so that's the empty set. There's nothing in common. So anytime you intersect the empty set with any set, you're going to get the empty set, because the empty set doesn't have any elements, so it can't have any elements in common with another set. Now let's look at trying to figure out what's in R and what's in S. So if I look at region 4, that's where R and S overlap. And so I notice that they do have D in common. I know that D must live in that intersection there. And then I need to place these other elements. In R, the only place left is 5 to place B, 1, and 3. And in S, I need to place C and E. And then I've got region 8 to figure out, so I need to figure out what elements live out there. A, I haven't listed yet. I'm looking through my universal set to see what elements I haven't listed yet. So A must live out here. B I already listed, C I already listed, D I already listed, E I already listed, capital A I haven't listed. 1 I listed, 3 I listed, 2 I haven't. So out in region 8 contains lowercase a, capital A, and 2. Now let's look at R union S union T. So this means take everything in R, everything in S, everything in T. So if we were to draw a Venn diagram, we'd have regions 5, 4, 1, 2, 3, 6, 7. So all of this would be in the union. So you're going to combine all elements in each of these regions. If it's in R, I'm going to list it. If it's in S, I'm going to list it. If it's in T, I'm going to list it. So R, I have B, D, 1, and 3, so that's for sure going to live there. And then S, I already have C, I've already listed D and E. And T doesn't have any elements, so we're not adding anything to that. And if you notice here, we've got C, E, S, D, or not S, sorry, that's the set S, C, E, D, B, 1, 2, 3. So that aligns with what we'd suspect from our Venn diagram. You don't necessarily have to use a Venn diagram here, but sometimes people like a visualization, so it's worth a shot. So R union S. So this means take everything in R, everything in S. And so actually this is the same thing as R union S union T, because we didn't join anything, we didn't add anything from T, because T is the empty set. So we just get the same thing. We get E, C, D, B, 1, 3. Now, R union S complement. This means take R union S. So this would be R union S. And then if you're taking the complement of that, notice how this bar is on the outside. So that means you take the union first and then take the complement. So we're going to take anything that's listed in region 8 and region 6. I know there's not listed anything in region 6 because T, that's part of T, and that's the empty set. So I'm only going to list stuff that's in 8. So R union S complement is going to contain 2 lowercase a and capital A. Now, R complement intersect S complement. Let's think about what R complement is for a minute. So R complement is everything outside of R. So we've got region 8, region 7, region 3, region 6, all those regions, okay? So let's write this. R complement contains regions, let's see what I've got here. 7, 8, 6, 3, right? And then S complement contains, let's shade this in. S complement is just everything, any region outside of S. So C is my S in this case, sorry. So everything outside of S is going to be region 5. Let's see, region 5, region 2, region 6, region 8. And I think that's it, right? 2, 6, 5, 8. Now, the only thing that they have in common, let's see here. What do they have in common? They have in common 6 and 8. Now that should look familiar, because if we shade that in, let's shade in 6 and 8 to see what's going on with it. If we shade in 6 and 8, so this part, and then everything outside, notice how we get the same shading as we got in part D. So this takes sets R and S, and then takes everything outside of it. So actually, this is De Morgan's laws for sets. If I take the union of two sets, I'll use the other notation here if you're more comfortable with this, that's the same as the intersection of the complement of both. If I look at regions 6 and 8, there's nothing in region 6, right, because T is the empty set. So all I have is 2A and capital A. So notice that D and E are the same sets. Now if I take S minus T, let's think about what this means. This means take everything in S and remove any parts of it that are from T. So this means that 1 and 3 would be removed, regions 1 and 3, and I'd only have left what's not touching T. So I'd only have 4 and 7 left. But notice that doesn't really do much because, you know, T doesn't have anything in it, so there's nothing to remove. So really, we just get S back. We get C, D, and E back because T doesn't remove anything from it. C, D, and E. Hopefully that helps you understand the homework. Let me know if you need more clarification on any of the grading or solutions here.